Now, let us consider triple or 3-dimensional integrals. Unfortunately, unlike 1D and 2D integrals, it is not possible to give a geometric interpretation to 3D integrals. For that, we will need to draw figures in 4 dimensions, and that is impossible. But without drawing any figures similar to 1D and 2D cases, we can still say that a triple integral of a function of the 3 variables represents a volume in 4-dimensional space. Sometimes the term hyperspace is used if the dimensions are more than 3. Extending the definitions of 1D and 2D integrals to 3D is quite straightforward. The Riemann sum for the triple integral of a function of 3 variables f of x, y, z is S equaling the summation of f of x I, y I, z I multiplied by delta v, the summation going from I to n. In this case, the domain of integration is a bounded volume V. The bounding surface, some surface gamma in 3D space. This surface can be specified by equation relating x, y and z, satisfied by all the points lying on the surface. For example, if the bounded volume is a sphere of radius a centered on origin, the bounding surface is x square plus y square plus z square equaling a square. In equation 8, delta V I is an element of volume surrounding a point x I, y I, z I lying within the domain of integration, and the value is f of x I, y I, z I of the function at that point. The sum is over n such points. We get the integral I by taking the limit n going to infinity as before, which is equal to the limit of s n going to infinity, and which is again equal to integral of f of x, y, z multiplied by dv over the volume V. Just as in the case of 2D integral, we can express the above integral as a triple repeated integral, which is I equaling integration of f of x, y, z dx, dy, dz, x limit going from a of y z to b of y z, y limit going from c of z to d of z, and z limit going from z equal to e to z equal to f. The order of integration is first with respect to x, then with respect to y, and finally z. Note carefully how the limits are applied to each integral. The limits of integration when integrating with respect to x are a and b, which are in general functions of y and z. During the integration with respect to y, the limits are c and d, which are functions of z, and finally, for integration with respect to z, the limits e and f are some constants. We can change the order of integration, but then we should also apply limits accordingly. For example, if we reverse the order of integration, that is with respect to z and y and x, we have I is equal to f of x, y, z dz, dy, dx, z limit going from e of x y to f of x y limit going from c of x to d of x, and x limit going from a to b.